Good morning, good morning, good morning. Today I'd like to start a little series about statistics. Recently I wrote a paper, and this is the paper because I printed out for myself to walk through this story that I would like to tell you. I hope you can see it. Well, someday, at some point it becomes clear. So this is the title, and this is written by me. Now, behind me you see a board with a lot of numbers on it. So to get bored, that's why it's called a board. A whiteboard in this case. A board is always to be bored, especially with a lot of numbers on it. But I'm going to run over it with you about the principle, and maybe I'm going to put the camera a little closer so you can see the numbers more clearly. Okay, where it's all about. It's the name is the mathematical probability. Is mathematical probability or chance the same as physical reality, the power of the average? That's the name of the paper. And I like to discuss certain things with you about this. Why the statistical numerical value of chance, of probability, is not the same as the physical reality which it tries to imply. I'm going to sit, in the first place I'm going to treat some basic statistical things with you, which is behind me on the board, and so on, so on, so on. So I don't try to do this in one video, because then the video becomes a little bit lengthy. So I try to keep this message, these videos short per subject. And I try to split these videos in 3, maybe 4 subjects, and so 3 or 4 videos about this whole subject. Okay, let's get started. I'm going to the side so you won't see me, but it's really important to focus on the board, to get bored. Let me see if maybe I shove it a little around, easier to, yeah, that's my phone, SMS message. Okay. Okay, well, let's talk about numbers here. Where is my pen? Oh, here. Well, you all recognize this as a Gaussian curve, which is basically it's theoretical. Not always. There is in this subject, it's not only theoretical but also practical. But usually, what you see, this is the theory. In general, what you see that this is the theory, but in reality, it will always turn out to be a skewed Gaussian curve, either this side or that side. That's most common, that it's reality. This is pure theory, and also in our experiments you're going to see that you're going to see that this is more of reality than this. But in general, for some processes, you can take this as a good approximation. Okay, also here you're going to see that. Now what you see here is the standard numbers in which the chances are given and the percentages are given. In statistics you have to do with standard deviation, which is 1 standard deviation, 2 standard deviation, and so on. If you want to find out how that's calculated, there's a load of stuff on the internet where you can calculate the standard deviation. I'm not going to do in that. I assume that you know how to calculate the standard deviation. Now, in statistics you use 1 standard deviation, 2 standard deviation, 3s, 1s, 2s, 3s, and so on, to determine a certain value of a certain property or so. The temperature of a room, the moist in your room, you name it, whatever. the length of persons, and so on, so on, so on, and stuff like that. And then you get some kind of distribution. Like I said, mostly like this or that, and this is the theoretical basis of that. This is the idealized situation. But in our example, this is a good approximation of what we will see in a moment. What you see is that with 1 as you get an 86% 27% of coverage in this area. Yeah. So that means that if you go to this side or to this side, then this represents a 1 in 6.3 chance that measurements are over there, and a 1 in 6.3 chance that they end up here. Now, if you have a 2s, so that's this distance, then you have a 45% of coverage of your measurements, which represents for this point in 1 to 43.9 chance of ending up here, or a 1 in 43.9% chance of ending up here. Well, that's done for a lot of numbers of the statistical standard deviation for one, etc. So what is general in science is accepted that everything beyond the 5 or 6s limit, and that's somewhere, this is 3s, so that's somewhere here, yeah, that everything about that is discarded, scientifically discarded, and is regarded as noise, statistical noise. Yeah, so that's what science does in general. So everything that's called an outlier. These measurements outside of 5s or 6s is called an outlier, and is discarded from the measurements that are being done and is regarded as noise. Okay. How they came up with the 1 in 6.3 is, well, you take 100% minus the 68.27 and some, there's a whole bunch of numbers behind it. You come up to 31.76%. So that means that either side, that both sides added together, they have a chance of 31.76%. That means also that you have each side has 15.85%. Yeah. Well, 15.85% is 1 in 6.3. Yeah, and I've done that so for all. So let me see. 2s will end up in a chance of 1 in 43.9 chance. 1 in 43 that you end up over here in that area, and so on, so on, so on, so on. Well, if you go to the 6s, then you have a 1 in what is it? 999 billion. No, million. 999. No, this is billion, million, whatever. Now, 900,000 something. So 990. So what close to 1 in a billion, or 1 to 1 in a billion. Now that moves on. 7s is 1 in 7.8 times 2 to the 11th chance, and so on. Okay. And 8s is somewhere in the order of magnitude of 1.76 times 10 to the 15th, and so on. Now, okay. We're going to focus a little bit on what happens with coins. That's over here. That's this one. Now let's assume we have a coin, equal coins which have a 50% distribution. It's an honest coin and a fair coin. So you assume that you have a 50% chance. That's never the case, and we will also see that in reality, that you always have something, a distribution like this, or a combination of the two. But what is the chance that all heads or all tails end up? Well, with one coin, there's a 1 in 2 chance, or a 50% chance. And so a point, it's either head or either tail, so 1 in 2, yeah? And so you're going to, that's 0.5. The log of that chance is this number, minus 0.301 something. Well, if you increase the number of coins, then the chance that all heads are up or all tails are up is going to decrease. It's going to be lower and lower and lower and lower. And this is the log of that chance. Yeah? Now, let me see. If you have 50 coins, all ending heads up or tails up, has the same as chance as S8 or 8S. So statistically, you're below the number of that you would statistically discard it, and so on, so on, so on. Well, we will look also at the 1,000 coins. You have 1,000 coins, and you will toss them all, and you are looking for the chance of what is the chance of ending all heads up or tail or all tails up, which is pretty small, which is 10 to the power of minus 301.03. That's the chance. Yeah. Now the thing is, this is the theory. Yeah. Okay. I've done these experiments for some in reality. That's this table. Go over here. Okay. I have done so in the beginning for 100 tosses, 100 coin tosses. Yeah. Now let me put it in the camera a little bit more. You don't need to see me. It's about these numbers. I'll try to. Yeah, that's better. You see the numbers instead of the reflection of the window. Okay. Now, if you have one coin, you expect a little bit of 50-50%, which is the case, 46 and 54. Yeah, and these numbers are real. I really tested this. Well, if you go up, you find a kind of this kind of distribution, right? That's what you also see. And if you don't believe me, you can use these numbers and toss them into a computer yourself, and then you get something like this. Now, what you also see is that in the end, if you look at the numbers, then it's going to be a combination of these two graphs, which is in reality, which happens so in reality. That means that this coin is not, the used coin, I used a certain coin, is not equally distributed. It's not a fair coin, so to say. But it comes close, and this theoretical model is pretty okay compared to what we have here, what we have the numbers over here. Now, what you also see, and that's the point that I'm trying to make here in the end, and also what the paper is trying to make, is that the more coins, this is the number of coins, the more coins you take, then the middle, the center, the average is going to push the extreme results, in which heads up or heads down are the result, the measurements, so to say. It's going to push it out, and no matter how much coins you take or how many tosses you do. In the beginning I used 100 tosses, as you can see here. If you add all these numbers up, you come to 100, 100, 100. Here I did 154 tosses. Here I did 176 tosses. Here I did 311 tosses. And here I did 195 tosses. But what you see is that the middle, the average results is claiming all attention, is drawing all attention to it. And what it does, it pushes the extremes out of reality on both sides. I mean, in the beginning you don't see that with a little less coins. You don't see that that effect. But the more coins you are using, the more that you see is that the average results are claiming all attention and pushes the extreme results like 20 heads up or 19 heads up and one tail up. It's being pushed out of reality. And here 17 heads up and 3 tails down and 3 tails up. And these extreme results are being pushed out of reality. And yeah, you can increase the number of tosses, but the result remains the same. The extreme results are being pushed out of reality. And that is increasing with, this effect is being increasing with the number of coins you toss. Well, here you see that if you look at the numbers, then you see in the middle, in the exact middle, you see that there's a peak here, there's a peak there, but in the middle it drops, the peak drops. So basically you get an additional separation of that either the heads up or either the tails up here. So you get a split of the result. So based on this you can conclude that the coin is not equally distributed. It's not a fair coin. That's what you can see from these results. But it doesn't matter for this experiment, because the main effect, what I tried to find out, was what happens with the extreme results, in which case the 24 tails are up, or the 24 heads are up, and 23 tails are up, and 1 head is up, and so on. The extreme results. Well, you see that the middle, the average, is catching all attention in these experiments, and that's the point that I try to make. Okay, this is the first part of the. I'm going to sit back over there. Well, this is actually the main point that I'm trying to make in this video, that and in this paper also, that the average results is drawing all attention to it. Suppose that you would be in a locked up room where there's air in it. The chance that all oxygen which you can live on is ending up only in one corner for you, out of reach, and you suffocate because of that, it's the same thing as here, the same idea that the extreme results in a statistical probability, statistical thing, it's not going to happen. It's not part of reality, because the middle, the average, that everything is spread all over, the oxygen is spread all over the room, is more common. It's drawing all attention to it. And that's actually the point I'm trying to make with this paper that I wrote. So yeah, that means that yes, it's correct. The mathematical probability is real. The numbers are real. I mean, the statistical probability, the statistical chance is correct. The statistical chance is reality. But that does not automatically translate in a physical reality of it. And that's the whole point of this paper. That, yes, okay, there is a statistical probability that an extreme situation like all the oxygen in one corner of the room, by spontaneous random chance, the statistical probability is real, but that does not automatically translate in a physical reality. That's the whole paper about. Okay, this is the first part of the video, and I'd like to see you in the next video, where this part of that mathematical reality does not always translate in a physical reality. Some other examples I'm going to show you over there. Okay, thanks for watching so far, and see you in the other video. Okay, hope you